So today we would like to talk about two-step regression. This is usually the case when you have more than one independent variable. And sometimes people call it stepwise regression, right? Which means that you would have one variable first and then you would start adding additional variables on top of the existing one, right? So here in this model setup, we see that right now we have two independent variable as well as an error term, right? So what we would like to do is actually given that we know how to do one variable case, right? The simple linear regression case, and then in this situation, then we would just express one variable by the other one, right? So therefore, we are going to break it up into two steps, right? So first step, we would like to model one of the independent variable by the second one, right? In this case, we would like to express x1 as a function of x2 plus some error term, right? So this function, you can write it as a general function such as f, but in particular in the linear regression case, then it would just be a linear combination of the x2 variable. And if you write it in the matrix form, then you're gonna just write the design matrix, right? And then multiply the coefficient vector. So as usual, the design matrix, the first column is always the constant column. And then the other columns are just independent variables. So every row is one observation, right? And then usually we have like n observations, right, in your sample. And usually the number of columns are just how many independent variables you would include in this regression. And then usually you will have to also add the constant column, the first column, right? So therefore, you write it in the matrix format and then plus an error term. So geometrically, we know that to do, let's say like a least squares estimator, right? It just means that, you will firstly, the whole design matrix, when doing your regression, you're just, like spanning the column space of this design matrix, right? So this is the column space. So basically, you construct using the columns of the design matrix to span it, and then to construct this column space of the design matrix. And then what you need to do is basically you need to find the projection, the projection within this column space of the design matrix, that this projection is actually closest to the data that you would like to model, right? So therefore, the distance between the projection vector you find in the column space would have the minimum distance to the data vector you are trying to model, right? So therefore, this residual vector will be the shortest distance, right? Having the shortest distance between the projection vector with the data vector. And it also means that this residual vector is going to be perpendicular to this projection vector. So to write it out in the mathematical expression, right? So to represent this this fact that the residual vector is perpendicular to the projection vector. It just means that the residual vector is orthogonal to every column vector of the design matrix. So therefore, this residual vector, it's orthogonal, it's perpendicular to the constant vector ones, right? And the residual vector is also perpendicular to the independent variable vector, right? And then if you actually write it out, just times it out, it basically just means that, all your just expand the dot product, right? And then so this one, right, it becomes this, right? And it's just, every one of these dot product is actually 0, right? So this one is the residual, right, is 1. So therefore, it also, like, geometrically, it means that the residual vector is, orthogonal to the constant vector, right? So, your constant vector could be this one here, right? So this is the constant vector here, and then like another one that also exists, because the constant vector exists in the column space of the design matrix, right? And then you would also have another independent variable vector, right? So this is the x2 vector, right? It also exists in the column space of the design matrix, and because your residual vector is basically perpendicular to the whole column space of the design matrix. So therefore, it's perpendicular to every single vector in this column space of the design matrix, right? So therefore, which also means that, you find, because you're this, so basically you are decomposing your x1 into 2 parts, right? So one part is this projection vector that you can use your x2 to explain, right? So basically you are decomposing the x1 variable by its components that can be expressed by x2 variable plus an additional part that cannot be explained by x2, right? Which is perpendicular to x2. Is this extra part that you haven't been able to explain, right, by your existing variable, independent variable x2. So therefore we would further in the second step, that we will further regress the rest of information in y, right, on this additional gamma 1 had this component in x1 that cannot be explained by x2. But when we are doing this step, this regress y, this data part on this residual gamma 1 part, without the information of x2, we cannot regress it with an intercept, because this gamma 1 vector, residual vector, right? It's just a vector that is perpendicular to a constant vector, right? So for that, it means that, so think about that, right? Like for this step, you're trying to regress y, this data vector on this residual vector, right? So essentially, you're trying to expression of function, right, of gamma 1 hat, right, this one, right, and then plus another error term, right, let's say E error term. So so this one gamma 1, right, so we will literally also write it as a design matrix, right, times, because in the linear regression case, we would also write write it out as, say, like omega, right? So this is coefficient, right? Let's say that. But you cannot have this this constant vector anymore, because we know that the column space, because this gamma 1 residual vector, right, it's perpendicular to this constant vector, right, which means that this constant vector cannot exist in the column space of this design matrix, right? So therefore we cannot have this constant column, which means that basically this parameter would not have a constant term at all. So we would just have I1 gamma all the way to gamma n 1, right? So hopefully that makes sense. See you next time.